So this right here is the diagram and calculations for my washer lab. So let me right into it. I'll start with the calculations. The diagram. So right here is the washer. This is the surgical blade. It's 64.5 centimeters from the table right here. And when it gets cut, it's going to be 34 centimeters from the table right here. And then the distance from the ground to where it's cut is 85 centimeters. And then we have got a predicted landing spot of 1.2 meters. But the actual landing spot was 1.3 meters. So let me explain how I got my predictions first. So the basic concept we used was the total energy in any given system stays the same. The conservation of energy, law of conservation of energy. So in the system right now, the only energy this washer has is gravitational potential energy from here to here. That is the only energy it has. Once we cut this string, some of this, and it goes all the way down here, some of the gravitational potential energy stays. When it gets cut here in that moment, it'll have gravitational potential energy from here to here, but some of the energy will also have been converted into kinetic energy. It won't lose that energy, it'll just be converted into kinetic energy. And we can use that concept to find the horizontal velocity at this point, which we can use to find the actual landing spot. So the equation for that is GPEI is equal to GPE2 plus kinetic energy. And the kinetic energy is equal to have one half mv squared, and we can use that velocity to find that v to find the velocity, which we can use to find the predicted landing spot. And we don't need to know the mass because the masses will cancel out. So the equation for gravitational potential energy is equal to acceleration due to gravity 9.8 times m times 0.645 times your distance. So GPEI is equal to 9.8 m times 6.645 meters, and then this one right here, and then our kinetic energy is 1/2 mv squared, and all of our m's are the same since it's the same washer. So now we take these variables and we plug them in here. We do our algebra, combine like terms, and then we get our velocity horizontal is equal to 2.445 meters per second. And now we can use this horizontal velocity, and we can basically turn this into a horizontal launch equation. We assume that our vertical velocity is 0 because when it swings from here to here, there's no swing up, so it's not cutting at an angle. So we just assume that the vertical velocity is 0 and that it's all horizontal velocity. And we also make the assumption that the distance travel. We also make the assumption that the horizontal velocity stays constant throughout. It doesn't become less due to friction or whatever. We assume that it stays constant throughout. So the distance traveled horizontally is dictated by the time, which is dictated by how long it takes the washer to fall to the ground, which is dictated by gravity. And so then to find the time, we can use a kinematics equation. Change in x is equal to VIT plus 1/2 AT squared. And we know that our horizontal initial velocity is 0. So then our change in the distance, negative 1.19 meters, which is a distance from where it gets cut to the ground. Now 1.19 meters is equal to 1/2 AT squared, and acceleration is acceleration due to gravity, which is equal to negative 9.8 meters. And then we solve for that, and we get 0.493 seconds. This is the time it takes for this washer to fall from where it gets cut to the ground. It takes it 0.493 seconds, and that is dictated due to gravity, which is, yeah. And then so we take this time right here, and then we can plug it into the equation. Change in x is equal to VT, because we assume that this right here, the horizontal velocity, it changes the same. So change in x is equal to VT. Change in x is equal to 2.445 times 4.493. Change in x is equal to 1.2 meters. That is the total distance it will travel in that time with this velocity right here. One reason we didn't, our predicted landing was 1.2 meters, but the actual landing was 1.3 meters. And one reason for this was we didn't account for the radius. And so we assumed that the washer would be released at where it was cut at the blade, but this is wrong because the blade could have cut the string, say, over here, but the washer would have been down here because this string was longer than the radius of this string was longer than how high up the blade was, if that makes any sense. So for example, this right here could have been 80 centimeters from here to here, so the radius of from here, so it would have cut from, say, it would cut here instead. So we didn't account for that. The washer would have been down here when the string reached here. we just thought that the washer would be here instead. So now the next time we did it, we accounted for that, and then we calculated the radius of this, and we laid it here. So then say the washer actually was released here instead. So we fixed our GPE to put that into our calculations, and then once we counted for the radius, we were actually much closer for our landing, like only 2 or 3 centimeters off instead of 10.